Hello, everyone who's joined us in this course. Welcome and thanks for coming. This course is an introduction to Banach function algebras. Anyway, when to want to work on Banach algebras, it doesn't matter which kinds of Banach algebras, you have to know some basic information on the general theory of Banach algebras. So the first part of my lecture is devoted to general theory of Banach algebras and the spectral theory, and then I attempt to cover the Gelfand theory for commutative Banach algebras. After that, I focus on Banach function algebras, and I try to mention basic concepts and important results in this field. And in the final part, I try to mention some classical nice results in the theory of function algebras to make connection between the algebraic structure and the topological structure of these algebras. Okay, for references, I can, for example, mention Zalasko, Banach algebras, and the Rudin. I mainly use Rudin function analysis. Of course, chapters 10 and 11 are devoted to Banach algebras. And of course, I use Morphy because I found some proofs here better to follow. That's why I will follow this book. And Banach algebras and automatic continuity by Dells. It's very interesting book. It's like a dictionary. You can find many things there, and then I think it's really a good reference. And for Banach function algebras, I mainly use a book by Leibovitz, but you may use, for example, Gamelin, Estot, Phelps. They are, of course, related to Banach function algebras. Of course, this book is also useful for Banach function algebras. And of course, here for function algebras, I use some papers because I say some results as general as I can in this mini course. So that's why I use some papers. Another paper I would like to mention here, of course, it's not a reference because it's just a brief overview of Banach algebras, but I want to mention it here. This one, why Banach algebra? This paper is expository paper by Ronne, and maybe I think 2012. And I like to mention here it's for a general mathematical audience. So I like to mention here. Okay, let's start with definition of algebra. Actually, a complex algebra is a complex vector space So when we have a vector space, we have addition and also a scalar multiplication between the elements of A. But with an algebra, we need to define another operation, which is multiplication between the elements of A. More precisely, this multiplication is actually a bilinear map, is a complex Banach algebra with a bilinear map. From A to A, this is map like this, A times A to A, which takes pairs A and B to AB, such that we have we have associative property. I mean that for each A, B, and C in A, we have A times BC is equal to AB times C for each A, B, and C in A. For example, the complex field itself is the simplest algebra. Of course, zero is another algebra, but we consider in the rest, we consider A is not zero. Actually, we exclude zero just as a matter of convenience. And so in the rest, A is not zero. And what's norm algebra and Banach algebra? If an algebra is equipped with a norm which satisfying a special property, which I say a little later, as it's called submultiplicative property, we say A is a norm algebra. So a norm algebra, okay. Yes. If A is equipped, algebra A is equipped with a norm which satisfying submultiplicative property, in the sense that norm of A times B is less than or equal to the norm of A times the norm of B for each A and B in our algebra. Then we call it a norm algebra. Then A with this norm is called the norm algebra. And such a norm is usually called a submultiplicative norm or algebraic norm. If A is also complete with such a norm, A is called a Banach algebra. So Banach algebra is a norm algebra like, for example, A and with this norm, such that norm is complete. Okay, so a Banach algebra is a norm uh, algebra. So we have an algebraic norm. I mean that we have submultiplicative property of the norm, and the norm is complete. And then we call it a Banach algebra. I want to say more definitions, but the first one I want to say now, it's not very surprising. I think you saw it before in algebra course. Anyway, A is commutative. It doesn't matter A is algebra, normal algebra, or Banach algebra. Or abelian if, as usual, AB is equal to BA for all elements A and B in A. You've seen it before in your algebra. And the last one, of course, a Banach algebra A is called unital a unital Banach algebra if, first of all, A has an identity like E, and with norm of identity element will require to be 1. Identity, it's an algebraic concept. I mean that for each A in A times E is equal to E times A is equal to A. And such element, if exists, it must be unique. And I say that norm of E is 1. Actually, in unital Banach algebras, we need to normalize the norm as identity element. You know, because the algebraic property, anyway, the norm of E, it's more at least 1, but maybe it's not equal to 1. But a little later, I say a theorem which shows that if the norm is not 1, don't worry, we can define an equivalent norm, and with the new norm, we have the norm of identity element is 1. So by moving to an equivalent norm, norm of identity element is 1, and we can say that an Banach algebra is unital. Okay, and the other thing I want to mention here, I consider complex algebras and then complex norm algebras and finally complex Banach algebras. But of course, we can consider algebras over other fields like real fields, and finally we have real Banach algebras, and real Banach algebras have also been studied. But we restrict our attention to complex Banach algebras. You know, when we go further, there are some differences between them, and I don't want to be involved with such differences. And even time doesn't permit me, and so I have to restrict our attention to just complex algebras. And you know, like Hilbert spaces, the theory of complex Hilbert spaces is richer than the real ones. So it's like works for Banach algebras. Anyway, so an algebras here are all of them are complex. Okay, now before just starting examples, um, I say one remark, that's when we have a norm space, the operations, I mean that scalar multiplication and also addition, they are continuous. When we have a norm algebra, the other operation, I mean that the multiplication is also continuous. So as a remark, I can say that if A is a norm algebra, then the multiplication is jointly continuous. It means that if an is a sequence in A goes to A and Bn goes to B, then the sequence An, Bn goes to AB. Actually, it follows from submultiplicative property of the norm because An, Bn minus AB. Let's add and subtract, for example, An, B. So from triangle inequality of the norm and submultiplicative of the norm, we have norm of An, norm of Bn minus B, plus norm of B, norm of An minus A. Of course, it goes to 0 at infinity. The other one are the same. And we don't have any problem because AN is a convergent sequence, and in particular, it's bounded. Anyway, the whole goes to 0, and finally, ANBN goes to AB. So, multiplication is a continuous map. And now I want to mention several examples, and most of them are examples for Banach function algebras. The first one, let X be a topological space. And CB of X is the space of all continuous, bounded, complex valued functions on X. So F from X to C such that F is continuous and bounded. With pointwise operation, I mean that the usual operation between the functions, for the first time I prefer to write it. If, for example, f and g in CB of X, and lambda in C, lambda f plus g is this function. And of course, f g of X, this function. Pointwise operation. And it's easy to see that this is an algebra, a commutative algebra, of course. And the norm here, we consider is subnorm or uniform norm. I think you saw it before in real analysis or maybe functional analysis. Supremum of absolute value of f of X all over all elements in X. And we know that CB of X with this norm is a Banach space. And I want to say that the norm satisfies submultiplicative property. And so we have a Banach algebra. Of course, it's not difficult, but let me show you for the first example with more details. F and G in C of X and X in X, then Fg of X according to the definition of subnorm, it is most supremum norm of F, and this one at most supremum norm of G. And it works for each X in X, so we can say that supremum norm of Fg is its most supremum norm of F times supremum norm of G. So we have an algebraic norm. So CB of X with supremum norm is the Banach algebra. And of course, it's commutative and unital. The unit element is the constant function 1. The other example I like to say, let's X be a locally compact Hausdorff space and we define C0 of X, the set of all continuous functions goes to 0 at infinity. In other words, f continuous function from X to C, and they're such that f vanishes at infinity. What does it mean exactly? It's like calculus when we go that f of X, when X goes to infinity, f of x goes to 0. It means that for each epsilon, the set of x in x such that absolute value of f of x it at least epsilon is compact. So it shows that at infinity, the function goes to 0. It means that for each epsilon, there is this compact set, and outside this compact set, f goes to 0. So it means that f approaching 0 at infinity. Again, every function here is bounded because, for example, let epsilon 1. There exists compact set outside this compact set is less than 1. And on this compact set, because of the continuity of f, we have f is bounded. There is no any problem. So every function here is bounded. Actually, it's a subalgebra of CB of x. Actually, if each subalgebra of Banach algebra is a norm algebra, and if it's a closed subalgebra like this, we have a Banach algebra. And again, we have another example of Banach algebra. And commutative because operations are inherited from CB of x and pointwise. But not necessarily unital. It depends on, of course, x. In general, CB of x is not, C0 of x is not unital. Actually, it's an easy exercise you can do and check that C0 of x is unital if and only if x is compact. So you can check that C0 of x is unital if and only if x is compact. Of course, when x is compact, because I've used this notation later, we write C of x instead of C0 of x, or even instead of CB of x. Here, and it's exactly the algebra of all continuous complex valued functions on x. Another example is the algebra of continuously differentiable functions. Okay. Let's n is be a natural number, and I the closed unit interval in R. We define Cn of I the set of all n times continuously differentiable functions. So every function here is there is the differentiable of order n, and nth derivative is continuous. Of course, with pointwise operation, again, is an algebra, so I can change it with algebra. And it's a subalgebra of C of I. If we consider norm from C of I mean subnorm, it's just a norm algebra, but not Banach algebra. Actually, because of Sturm-Weierstrass theorem, Cn of I is dense in C of I, and so we have just a norm space, not Banach space, and so we have we have just norm algebra. I think you've seen the norm, which makes its Banach space. And here I want to make it a Banach algebra. I define a norm similar to that I think you saw before. Anyway, I consider norm like this. Norm of F as the summation of supremum norm of I's derivative over I factorial, I from 0 to n. Of course, I think that you've seen such a norm before, but without factorial. Of course, they are equivalent. And so again, Cn with this norm is a complete metric space, and so Banach space. But because we want to make it a Banach algebra, we have to put numbers here, 1 over I factorial. These coefficients are necessary here to have algebraic property. Otherwise, maybe we lose this property. For example, let's just a moment. Let's n is 2, and f of x is identity function. And without these coefficients, we have norm of f is supremum norm of f plus supremum norm of f prime plus supremum norm of second derivative. And so for f, we have norm of supremum norm of f is 1, supremum norm of f prime is 1, and the second derivative is 0, so we have 2. And so for f2 of x, we have x power 2, and so norm of f2 will be supremum norm of f2, okay, 1. Supremum of first derivative is 2, and second derivative is the constant function 2, again 2. So we have 5 here. And according to this property, we expect to have this inequality, which is impossible. So it shows that those coefficients are necessary to give us an algebraic norm, and we have this property. But because it's equivalent with the norm you saw before, it's also a complete norm. I just want to show that we have this property, and finally we obtain submultiplicative of the norm. Okay. So I can see the f and g in Cn of I, and I want to show that the submultiplicative property. Norm of fg, according to the definition of norm, we have I from 0 to n, supremum norm of fg, I's derivative of fg over I factorial. And according to the formula for the derivative of two functions by induction, we can obtain that this is sigma of fr as derivative of g r plus a. S is I over I factorial. Sorry, I forgot to, for example, R or S, it doesn't matter which one, but we need to put it here. Okay. Okay, according to the formula for I choose from N, we have I factorial, R factorial, I minus R factorial, which is S factorial. And if we use sub-multiplicative of the sup norm, we have, this is at most sigma of norm of FR, R factorial, all from 0 to N, and this one. Supreme norm of S derivative of G over by S factorial S from 0 to N. Of course, here even we have more terms, and then this is norm of F, and this one is norm of G. So this norm is an algebraic norm. Of course, I factorial is omitted here. That's why I didn't write it. Anyway, so again, see N of I, we have another Banach algebra with this norm is a Banach algebra which is unital and commutative. The other example I want to mention is Lipschitz algebras. Actually, Lipschitz algebras are really rich, and there are vast literature concerning such algebras. You can find a book by nice book by Weaver. Just this book deals with Lipschitz algebras. But I just mentioned special case of Lipschitz algebras as another example. Let X and V be a metric space a function f from X to C is called Lipschitz on X if there exists a scalar like M such that the absolute value of f of X minus f of Y that most M times d of X and Y for each X and Y in X. So it's clear that each Lipschitz function will be continuous. And so it's with pointwise operation, it's a subalgebra. It's not difficult to check that it's a subalgebra of C of X. But if we consider subnorm, again, because of Stone Weierstrass theorem, we have just density of Lipschitz algebra in C of X. So we consider another norm. But before that, let me write exactly the Lipschitz algebra. Lib of X is the space or the algebra, algebra with pointwise operation. Is the algebra of all Lipschitz function on X. So it is the algebra of Lipschitz function, and I told you This is a subalgebra of C of X, but because of Weierstrass theorem, it's dense in C of X. And it depends on X, of course, but in general, it's just a normal algebra, but not necessarily Banach algebra. So we consider another norm, which is called Lipschitz norm. But again, with pointwise operation, so it's commutative and unital. The unit element is, of course, the constant function 1, and you will see that the norm of this element is 1. Uh, if f is a Lipschitz function, we define Lipschitz norm like this: supremum norm of f plus L of f. Actually, L of f is the smallest m satisfying that property. So, and so it will be supremum of absolute value of f of x minus f of y over t of x and y for each any distinct points in x. Uh, Usually it's called the Lipschitz constant, or the Lipschitz number of f. But anyway, it's the least number satisfying those properties. Uh, I want to show that this is a complete norm, and also it satisfies submultiplicative property. I show the second one first. I mean that I show that it satisfies submultiplicative property. Let f and g in lib of x. So if x and y in x and but distinct, so we can write f3 of x minus f3 of y over d of x and y. Let's, for example, add and subtract f of x, g of y, for example. And so from triangle inequality, we can say that f of x, g of x minus g of y over the x and y plus the other one. G of y is the same. And finally, we have f of y minus f of x, or f of x minus f of y. According to the definition of subnorm, it at most subnorm of f, and this one at most subnorm of g. And this one, it at most Lipschitz constant of g, and the other one Lipschitz constant of f. So finally, we get supremum norm of f, L of g plus supremum norm of g, L of f. But first, for any distinct points in x. So finally, we can say that f and fg, of course, in lib of x, and norm of fg is, which is supremum norm of fg, sorry, plus L of fg. This is supremum norm, so we can say that it's at most supremum norm of f times supremum norm of g. And L of fg, if we get supremum here, we can say that at most supremum norm of f, L of g, plus supremum norm of g, L of f. And this is exactly norm of f times the norm of g. And finally, we get submultiplicative property. Now, it remains to show that this is a Banach space. So we consider a Cauchy sequence, and we show that it is convergent in lib of x with Lipschitz norm. Okay. Let Fn be a Cauchy sequence in lib of x with norm of Lipschitz norm, supremum norm plus Lipschitz constant. So for each epsilon, there exists natural number like n, such that for each m and n greater than n, we have norm of, according to the definition of Cauchy sequence, just write it here, is less than epsilon. It means that supremum norm of fn minus fn plus Lipschitz constant of fn minus fn. So for each epsilon, there exists a natural number such that for m and n greater than n, supremum norm of fn minus fm is less than epsilon. So in particular, we infer that fn is a Cauchy sequence in C of x with supremum norm. So it shows that fn is a Cauchy sequence in C of x and supremum. But we know that this is a complete metric space, it's a Banach space. So there exists, because C of x is Banach space, there exists f in C of x such that supremum norm of fn minus f goes to 0. Okay, we need to show that f is also Lipschitz, and we have this convergence with respect to Lipschitz norm. Okay, I use this inequality. It means that for any testing points in x, we can say that fn minus fm at x minus fn minus fm at y all over d of x and y, according to the definition of L of function, the Lipschitz constant, it at most L of Fn minus Fm, and we know that this is less than epsilon, of course, when m and n is greater than n. Okay. Fix n and let m go to infinity. And because of this, fm of x goes to f of x and fm of y goes to f of y. So we have fn minus f at x minus fn minus f at y over d of x and y, it at most epsilon. Of course, for n greater than n. It works for each x and y, different points in x. According to the definition of Lipschitz constant, we get supremum over all these elements. We get L of Fn minus F is at most epsilon. Okay. Okay, we arrive here. Just according to the definition of L, the Lipschitz constant of Fn minus F is at most epsilon for n greater than n. In particular, it shows that, for example, Fn plus 1 minus F is a Lipschitz function. So it belongs to lib of x. And then Lipschitz algebra is a vector space. So finally, this function is Lipschitz. And from this relation, we can say that L of Fm minus F goes to 0 at infinity. And finally, Fn is a convergence sequence in lib of x. With Lipschitz norm. With supremum is in general just a norm algebra, not necessarily Banach. The other example I'd like to tell you let X be a norm space, and I consider B of X. Definitely you've seen such a space before in real analysis. B of X is the space of all linear operators on X, which are continuous or bounded. They are equivalent. So is the set of linear maps from X to X such that F is continuous or continuous. Bounded in the sense that, and the norm is, we consider here is the usual operator norm. It means the supremum of norm of T of X This is the norm in X. Over all those elements in X, the norm of X is at most 1. It doesn't matter if we choose elements in X in the closed unit ball, just the unit sphere or the interior of unit ball, doesn't matter. They're the same. It's easy to check. And this is operator norm, and we know it as a vector space with pointwise addition and pointwise scalar multiplication. But if we want to make it a Banach algebra, we define multiplication to be composition of function. I mean that if S and T in B of X, ST means SOT. And this is but this no let's okay. This is an algebraic norm, and so another example of norm algebra. You know that B of X is Banach space if and only if X is a Banach space. But just right here normal space, so B of X is a normal space. Norm algebra, sorry. Because the operator norm is algebraic norm. For example, S and T in B of X, and X in X, norm of S T of X, it means that S of T of X according to the definition of operator norm, it's really easy to see that it at most norm of S, norm of T of X. Again, definition of operator norm for T is the norm of S, norm of T, norm of X. Because actually this norm is the supremum norm of T of X over X. X is not 0. Anyway, it works for each X, means supremum on those elements in the closed unit ball. We get norm of ST. It has most norm of S, norm of T. Then B of X with operator norm is an example of, another example of norm algebra here. Of course, if X is Banach space, so we have X is a Banach algebra. And you know that's infinite dimensional when dimension X is n, is actually isomorphic to B of X, is isomorphic to, as in, so it's in linear algebra, isomorphic to Mn of C, the algebra of complex n times n matrices. The algebra of all n times n matrices with interest in C. And this is of course, P of X is the unital Banach algebra. The unit element is the identity operator, and the identity operator has the norm 1, and so it's unital, but not necessarily commutative. It's just commutative if and only if dimension of X is 1. It means that B of X is just C. So B of X is commutative if and only if X is one dimensional. So it's an example of the other cases when dimension is greater than one. We have example of non-commutative Banach algebras. And here I try to say all examples I want to say. Of course, most of them are examples of Banach function algebras, and then later I want to use them. Okay. Another example. Um, I want to consider the compact operators, the subalgebra of B of X. You know that if X is a Banach space, curve X, I mean that the set of all compact operators on X is a subalgebra of B of X. Even it's an ideal and a closed subalgebra, so itself is a Banach algebra. Another example of Banach algebra. So if with inherited operations and norm is again operator norm. If X is the Banach, sorry, Banach space, the closed subalgebra K of X of B of X consisting all compact operators on X is a Banach algebra. So this is another example of Banach algebra. And another example, um, it's a subalgebra of continuous algebra of continuous function and the closed unit ball of C. Let D, for example, it's a unit ball in C. I mean that lambda in C such that the absolute value of lambda is at most 1, which is a closed subset of C. And AD is the algebra of all continuous functions which are analytic on the interior of D. Okay, so f from X to C, f continuous, and f, there is section of f, and the interior of D is analytic. It's a subalgebra of C of D. And since the uniform closure of each analytic functions will be analytic, so it's a closed subalgebra of C of D. So with a uniform norm is a Banach algebra. And of course, it is commutative as unital because we have constant function 1 here. Actually, each function here is a uniform limit of polynomials. Because, for example, if f in A of D and for each epsilon positive epsilon. For example, I'll define f of epsilon like this. H lambda, f of lambda over 1 plus epsilon. This is analytic in on the open disk like this, lambda in C, such that the absolute value of lambda is less than 1 plus epsilon. And so because of Taylor series, f epsilon is the uniform limit of polynomials uh, of course by Taylor series. And since f epsilon goes to f when epsilon goes to 0, since we have supremum of fn, f epsilon minus f goes to 0 when epsilon goes to 0, f is the uniform limit of polynomials on D. Actually, AD is generated by 1 and Z identity function. I mean that Z or coordinate functions that are lambda is lambda. I mean that because each polynomial is a linear combination of powers of Z. So we have another example of Banach algebras. And now the last example. Sorry, here is not. Uh, uh, L1, but little L1. I mean that L1Z, you know this space in real analysis, of course, definitely you've seen it before. Anyway, it's a set of all sequences like AN indexed by Z such that summation of absolute value of Fn is less than epsilon. Uh, we know that L1 with this norm of A or AN is this summation exactly. With pointwise addition and of course pointwise scalar multiplication is the Banach space. I want to make it a Banach algebra. I define multiplication like this. We define the multiplication to be convolution, which is defined as follows by this formula. A star B is a sequence like C such that n entry is sigma AK Bn minus k from minus infinity to infinity. Of course, when A is in L1, this is bounded. And so this and B is also in L1, so this summation is well defined. Anyway, when I want to check that the norm is submultiplicative, so we see that this is also in L1. But anyway, it's apart from the submultiplicativity of the norm, you can see that it's well defined. Anyway, we show that norm is algebraic norm with this multiplication. Let A and B in L1 and the norm of A star B is the sigma of this element. Cn, okay, like Cn, and from minus infinity to infinity. And if we replace Cn is here, we have k, b, and minus k. And we can use triangle inequality, and finally we get they're non-negative numbers, so it doesn't matter if we want to change the order of these to summations. I change it because I want to take out the absolute value of a con. Okay, let's write it here if it's possible. I think it will be possible. Anyway, okay, I changed the order, and we have k, and here n, and I take out a co, and the other b n minus co. For each k, it's n minus co is from minus infinity to infinity, so this is norm of b. And this one again, it can be taken from this sigma, and this is exactly norm 1 of A. So we have norm 1 of A, norm 1 of B. So we have a submultiplicative property of the norm. So it's another example of Banach algebra. And of course, commutative, because it doesn't matter, there are elements in C, the scalars in C, and so there's no matter if we change, for example, here, A and B. So it's commutative, but Unital, yes, it's unital, of course. The unit element is D. Like, let me apply some notation like canonical symbol, delta zero. This is a sequence. At zero is one. The other entries is the other entries are zero. Actually, this is at zero is one, and for other entries is zero, and n is not zero. So this is unit elements because the only thing can be here, for example, when k is zero, and this is exactly Bn, this one a0, I mean that's the unit element, this is one. Of course, it gives you just Bn for n entry, so there is no problem. This is unit element and normal. This element is one. But maybe you ask what happened with the pointwise multiplication. Actually, again, we have a Banach algebra. I mean that even pointwise multiplication turns it to be Banach algebra. And even it's easier to check that, for example, we have a submultiplicative property of the norm. So with pointwise multiplication is also another example of Banach algebra. But of course, it's not unital. It's different. It's not unital, of course. And okay. Actually, let's one remark. I say convolution as an multiplication because I want to mention group algebras. If G is a locally compact group with a left half measure and L1 of G, the Lebesgue integrable function as usual, and normal is exactly as usual. We say, for example, F here, norm 1 is the integral of absolute value of F on G with respect to, for example, half measure lambda or, for example, mu. Here there is usually lambda for a scalar. And convolution like this. I don't want to go in details because it's some information before about, for example, half measure and locally compact group. But anyway, with Fubini's theorem and using left invariance of half measure, can be seen that this is a Banach algebra with this convolution. Okay, and that's why I use L1 to consider as an example of group algebra. And of course, group L1 of G is not necessarily unital. It's unital if and only if G is discrete, like our example. Okay. Now I finished the examples, but as I promised you, I told you if we have a Banach algebra with identity and the unit element, the norm of this identity element is not one, we can consider an equivalent norm, which make it a unital Banach algebra. Actually, identity element is called unit element in unital Banach algebras. Anyway, so I went to this theorem. Okay. And let A be a Banach algebra with unit or by its identity E, then uh, there is an equivalent norm which makes it a unital Banach algebra, makes it unital. Okay, what's this equivalent norm? For proof, for each A, in A, we define left multiplication operator. We define for each A. I mean that this operation, M of A, from A to A, which takes B to AB. And this is actually a linear. It's easy to check. It's linear and bounded because the operator norm, which is the supremum of M of A, sorry, of B, norm of B at most 1. So we have supremum of AB, norm of B at most 1, because we have a Banach algebra, so we have some multiplicative property of the norm, and I take out norm of A. So this is norm of A. As I showed you, algebras are not zero. So M of A, and so the set of M of A in A is a element here is in B of A, and exactly the set of this left multiplication operators is a subalgebra of B of A. Example 5, I think. Subalgebra of B of A. I mean that the bounded or the continuous linear operators acting on A, because it's easy to check that. For example, M of A, M of B is equal to M of AB, and lambda M of A plus M of B is equal to M of lambda A plus B. So it's a subalgebra. Also, we have, according to the definition of operator norm, we can say that norm of M of A is at least norm of M of A, but we apply it at this point, E over norm of E. And this is AE over norm of E. Norm of E is constant, and the AE is also E. So this is finally norm of A, norm of E. And then norm of E, norm of M of A, is at least norm of A. It shows that it's combined with this relation. we can say that norm of M of A and this norm are equivalent somehow. I say it now precisely. Anyway, we define. It's clear that what is the equivalent norm? We define norm of A, the new norm, to be norm of M of A for each A in A. And so this is subalgebra of B of A. So this norm is algebraic norm. And it's a closed subalgebra because these norms are equivalent. And unital because actually M of E is the identity operator and the norm of identity operator is 1. So anyway, we have a Banach algebra, unital Banach algebra. Okay, then A with this norm, which is equivalent to the first norm of A, is a unital Banach algebra. As I told you, identity element is actually M of E. And the norm of this element is 1. Okay, so by moving to an equivalent norm, we can normalize norm at identity element or unit element. Okay. In the rest, I want to consider just unital Banach algebras. But, you know, when we have non-unital Banach algebra, every non-unital Banach algebra can be embedded in a unital Banach algebra. So every concept I tell you later can be extended to non-unital case because each non-unital case, non-unital Banach algebra can be embedded in unital Banach algebra. Anyway, so assume that A is with, for example, with this norm, is a non-unital Banach algebra. I want to define an embedding. Let's similar here. Yes. 18 B A plus C. There's some lesson. I mean that it's the vector space of the direct sum of A and C. 18 is a vector space with coordinate-wise operations. I want to make it an algebra and then Banach algebra, I define norm. So I define multiplication like here. Actually, the pointwise multiplication is not useful because again, we don't have any unit elements. So we define multiplication as follows. Sorry, this is consists of all uh, order pairs A and alpha, A in A and alpha in C. This nice multiplication AB plus alpha B plus beta alpha, and the second element in C in alpha beta. And the norm I consider is normal. Each element is norm of A plus absolute value of lambda. It's really easy to check that 18 is a Banach algebra with this norm and unital. The unital Banach algebra with unit element is 0 and 1. In fact, if A is a norm algebra, it will be norm algebra, but because I wrote Banach, so we have Banach algebra. There's no difference. And this is a common method to make a Banach algebra be a unital Banach algebra, which is not unital. Make it, can embed it to this unital Banach algebra. Actually, the map here, the map from A to 18, which takes A to and 0, is the embedding, is an isomorphism A onto a closed subalgebra of 18, whose codimension is 1. We don't have C, of course. So whose codimension is 1. So actually, the image of this map can be considered as the maximal ideal of a field because the codimension is 1. So if, for example, identify A with A and 0, we can say that AT is just A plus one-dimensional vector space generated by unit element E. I mean that the difference is just the one-dimensional vector space and nothing more. That's why we can extend concept from unital case to non-unital case. And for the rest of the lecture, because of the time, I have to consider just unital Banach algebras. And anyway, this 18 is called the unitization of A. T is called the unitization of A. So in the second this lecture, all Banach algebras are unital. But the method you can extend the concept to non-unital case is using this unitization. Are unital Banach algebras. I say some concept in the theory of Banach algebras because I want to say a spectral theory for these structures. The next is characters. Characters and character space of Banach algebra. What's the character actually? Let's write definition. A non-zero homomorphism like V from A to C is called a character on A. So it's each character is a non-zero linear function or which preserve multiplication. I mean that phi of AB is equal to phi of A, phi of B. And of course, because it's linear functional, we have this. But if we consider just non-zero and we exclude zero homomorphism, just it's matter of convenience and nothing more. So any character is a non-zero homomorphism from A to C. And we put all characters on A in this set, M of A. Of course, maybe some books, for example, for example, phi of A or omega of A, but because then in commutative case, there exists a projection between elements here and the set of maximal ideas of A. So I prefer to use M of A. So M of A is D from A to C. D is cat. And is called the character space of A. And there's another definition which is not very difficult because you definitely saw it before in your algebra. And definition of invertible element. An element A in A is invertible if there exists an element in A like B such that we have A times E is equal to A times B is equal to B times E is equal to E. This element B is unique. If we have it, is unique. This element B is unique and is and usually is denoted by A inverse. I don't know if it works well or not. Uh, and we set all invertible elements in this set. A inverse is the A in A such that A is invertible. The set of all invertible elements. Some books use, for example, inverse of A. They use A inverse. Actually, A inverse is a group with multiplication. And it's easy to see this fact. Okay. Um, A inverse is a group because if A inverse A and B if A and B are invertible, then, for example, A minus B is invertible, and because inverse is B is called also inverse of A. A minus 1. So A inverse is a group, the set of invertible elements. And just finally say a proposition. It's really simple proposition. And if P in M of A, then P of identity element is always 1, and P of each invertible element is not 0. Okay, why? It's really easy. Of course, P is M of A, so it's not 0. So there exists element like B in A such that P of B is not 0. P of B, we can write B like B and E. So Bbb P of E, and we know that it's not 0. So P of E is 1. And for invertible elements, if A was an invertible element, then we know that P of E, which is 1, and E can be written like A inverse. P preserve multiplication. So P of A is not zero. But not only phi of A is not zero, but we can infer from this equation phi of A inverse is the inverse of phi of A. There are elements scalars in C. But there is some examples which some Banach algebras, unfortunately, the character space maybe is empty. I think for you, not, it's not very difficult. But anyway, for example, for Mn, you can see character space is empty because only homomorphism on Mn will be zero. And that's why M of A is non-empty, is empty. But for a commutative case, for all of Banach algebras, M of A is not zero, and also there exists a very nice connection between these elements and maximal ideals of A. Okay, I finished this lesson now because I went to tell you on another uh, theorem, but I think it's better to leave it for tomorrow, the next session. It's really handy in our proofs, and so I prefer to say it tomorrow. If you have any comments or questions, please write to me, and this is my email address. I can write it here. And that's HOSSEINI @KNTU.ac.ir. Okay, thanks everybody, and have a nice day. Bye.